All right, so here I want to give you a sneak peek or a little introduction into the matrix equation. And what the matrix equation is going to allow us to do is to check that unique solution we found using what is called the matrix equation. So the matrix equation is defined as matrix A times vector X is equal to vector B. And now this is where this matrix A is the coefficient matrix. Vector X is the general solution. That's your solution vector. And vector B is simply the constant vector. Or in other words, the right-hand side of your linear system. That is the right-hand side of the system. The right-hand side of those equal signs. One more fun fact here before we look at how we can use this to check. This matrix equation is equivalent to the augmented matrix. So this is the same thing as saying matrix A augmented with that constant vector. So this is an important equivalence that is going to follow us for the rest of our mathematical lives. So let's explore how we can use this to check our solution. So to do that, I want to think back to the previous example. So remember, in our previous example, we were asked, or we were given this beautiful system here, and we found this general solution. So how can we establish the matrix equation? Well, let's break this up into piece by piece. And I'm going to break this up into a little extra detail here because it's going to be important for us to decompose a linear system. We need to know all the ins and outs of our system. So showing a little extra detail here. Again, looking at the system, we have three defined columns. You have your x sub 1 column, your x sub 2 column, and your x sub 3 column. Well, I guess technically we have four defined columns. You have the fourth column of your constant vectors. So let's break this system up into a linear combination of the variables. So I'm going to break this up into what we call a linear combination. And it's a linear combination of each one of these variables. So your first column vector, so I'm going to pull that x sub 1 out, because I have that scalar multiple of x sub 1 here. So this becomes x sub 1 multiplied by the constant vector 1, 2, 4, plus, moving on to that second column, notice how it has a scalar multiple of x sub 2. So this becomes x sub 2 multiplied by the constant vector of coefficients 2, 4, 5. Moving on to our third column, notice how this column has a constant scalar of x sub 3. So we can pull that common scalar x sub 3 out in front and multiply it by the column vector of coefficients 4, 5, 4. And this is equal to the constant vector on the right-hand side. That's negative 8 minus 10, negative 11. So we have a linear combination, of course, we should include, such that x sub 1, x sub 2, and x sub 3 are your scalars. So you have a linear combination of these three column vectors, where these x sub 1, x sub 2, x sub 3 are our scalars. This format that we have here is called the vector equation. And this is also going to play a part in checking our general solution. Now, notice, if you think back to that augmented matrix from this example, we can see the column vectors of that matrix, of that coefficient matrix. They're these constant vectors. So what we can do is put those three vectors into a matrix, into that coefficient matrix. So putting that into the matrix, the first column is 1, 2, 4. The second column is 2, 4, 5. And your third column is 4, 5, 4. And now what we're going to do is take these three scalars, x sub 1, x sub 2, x sub 3, and put it into a vector. So this is the vector x sub 1, x sub 2, x sub 3. And that is still equal to that constant vector on the right-hand side, -8, -10, -11. And this is what we call the matrix equation. So this is the matrix equation. And you can see the definition of the matrix equation coming in here. We can see here's matrix A, the matrix, the coefficient matrix. Here is vector x, the solution vector, and it's equal to that constant vector, those constants on the right-hand side of your equation. So we use this to check the solution vector that we found at the beginning, or that we found in the previous example. So if you've seen matrix algebra before, you may think to yourself, this is not the most efficient way, and you are correct, but this is what establishes the faster ways to solve. So we need to see this one time through. So here we want to check our general solution. This helps us to understand and analyze these systems. So we want to check the general solution. We need to make sure that if we take this coefficient matrix that we just established and we multiply it by that general solution, -2, 1, -2, we need to make sure that is this in fact going to be equal to the constant vector, that vector b on the right-hand side. So we check this with our matrix equation, and we're actually going to decompose it back to this linear combination format. Oops. So we want to check this, or re-decompose it to that form. So here we go, and I'll try to keep everything so you can see how we're checking. So we can re-decompose this to -2 multiplied by that first column vector, 1, 2, 4. And now we want to add this to 1 of the second column vector, 2, 4, 5. And then we want to add this to -2 of that third column vector, which is 4, 5, 4. And again, we're still asking ourselves, we're not sure yet, is this in fact equal to -8, -10, -11? So let's find out, let's make sure that our algebra in the previous example was accurate, and that this in fact is the solution. So giving ourselves plenty of room here. We have a little vector arithmetic. So this first case is -2 times that vector. So this is going to be equal to -2 times 1 is -2, -2 times 2 is -4, -2 times 4 is -8. Plus, now we have 1 times the column vector, so this is just that same column vector, 2, 4, 5. And now we're adding this. We have a scalar multiple of -2 times this third column vector. So we have -2 times 4 is -8, -2 times 5 is -10, -2 times 4 is -8. And let's add these together. So adding up those like components, we have -2 plus 2 minus 8 in the first row. We have -4 plus 4 minus 10 in the second row. And the third row is -8, 5 minus 8. And let's see, what does this give us? We have the 2's cancels and we're left with -8. The 4's cancel and we're left with -10. And then we have -16 plus 5 is -11. Woohoo, which is what we wanted. Hooray! So this lets us know that, yes, this is the accurate solution. So we have confirmed that vector x is actually equal to -2, 1, -2. This is the correct, unique solution to our system. And we've helped ourselves to better understand the decomposition of a system with the linear equation format, your vector equation format, and the matrix equation format, as well as the augmented matrix. They all mean the same thing. So get excited for next week's lecture on the vector equation, the matrix equation, and their equivalence properties.